on this computer. All right, we are now recording. Okay, this is review session for chapter 2 tests. So let's begin. What questions can I answer? Do a little dance while I wait. Ooh, no, oh no. Do we have any questions? Mark, you might be in luck. Maybe we'll get to start with your question right away.
Well, to be on topic of chapter 2, we could go over problems where you have to prove identities using like definitions.
Yeah,
sets.
We could go over one of those. So let's start with one of those, sure. And then I've also got a request in the chat here to go over something from section 2.5, which would be like, cardinality. Okay, so since this is about the oh, and here we go, 2.5 number 18, good. Since this is going to be you're only going to have an hour, I'm not going to include very long proofs. So for example, on the test, I might ask you to prove that something is injective or prove that something is surjective, right? So kind of like the problems on your assessment, where I gave you a function. I said, is it injective or surjective? Which one is it? Yes or no for each, and then prove, right? So something like that. However, referencing another problem from the assessment, the one where I ask you to prove that this complicated set is a subset of another thing, like the one about proper subsets, remember? Like a proof like that would be on the take-home part, because that is a little longer and more involved. So let's, oh my gosh, okay, we actually have a lot of questions. Let's start with what Mark suggested, do one of those proving like a set identity. I'm just going to pull one up here. I'll share my screen in a moment. Okay, I'm going to go ahead and share. So here's an example of a set identity. A union B minus A is equal to A union B. So let's start with that one. A union B minus A is equal to A union B. So to prove this, you could start with the left side, A union B minus A. Now let's use essentially a, I'm not sure this one is actually on your reference sheet, but B minus A is equivalent to B intersect with A complement. Okay, B intersect A complement. That is like an equivalence with subtraction. The idea is if you're subtracting out just the elements of A, then what you could do instead is say where are you overlapping with the complement of A, right? Like here's B and here's A, B and A. If you're subtracting off these ones, then the question is where do you overlap? Where are you outside of A, right? Overlapping with the exterior of A. So that we'll just say basically by a definition. I'm not sure that's on your reference sheet, but we'll take that as given. Then you can use the distributive law, A union B, subset with A union A complement. That's distributive, right? And then you can use things like the negation law. So here in this one, this is this A union A complement is the same as the entire universal set. That is the entire universal set. That's the negation law. And the reason for that, remember, is just that A and A complement together form everything, right? It's like A and A complement are kind of like a proposition and its negation. A proposition or a negation are one or the other has to be true. So if you say like P or not P, that's a tautology. It's always true. And the always true tautology proposition is equivalent Like it plays the same role as the universal set in set theory operations. So this universal set now that we have intersection with universal set. This is just like you had like sort of and true. Okay, it's just like and true, which is an identity operation. If you say p and true, that's equivalent to just p, right? That's like times one. So so basically the intersection operation is playing the role of and. The universal set is playing the role of a tautology t. And this whole thing is an identity operation, which leaves us with just A union B. I don't need parentheses any longer. That's identity. That's an example of proving, so there we've proven this using the set identities, right? Questions on that one?
It seems pretty similar to what we did before, but just like the symbols are different.
That is exactly true, I would say. Yeah, in fact, the logic is identical. Like, you know, everything has its equivalent. There's and or, which are the same as, which play exactly the same role and follow all the same rules as intersection and union, right? There's tautologies and contradictions. Tautologies are the universal set. Contradiction is the empty set, right? Like they play the exact same role. They're totally analogous. And so, yeah, it seems similar because it is pretty much identical with different symbols, as you say. Yeah, that's part of what's cool here. I think it's just really neat that like it's a entirely different context, and yet the algebraic structure is identical. This is called a Boolean algebra. You can actually generalize it to lots of different situations with different operations on different sets. And if they satisfy a certain number of rules, then you can say that it's like the same structure. It's called a Boolean algebra. So let's take a look now, I think, at functions. Let's turn our attention to functions. So there's been a request to go over domain/codomain. So let me just review what that means. And then we'll look at and then actually that might be all, because then the other questions are about 2.5. Is that right? So far? Yeah. So quick review of functions here. I'm going to clear the screen. Also, I'm going to switch colors because I don't like this green. I like this green for some reason. It's bugging me. Let's go to blue. All right, so a function. This is the domain. And this is the codomain. So it's really important when working with functions to remember that the codomain is not necessarily the entire range. Not necessarily range. So here's an example. Let's say you have a function f that goes from the integers to the integers. This is an example that's fresh in my mind because I was just talking to someone about this one. Let's say it goes f of n is 2n. Okay, f of n is 2n, 2 times n. So let's write some integers. Let's say it goes -2, -1, 0, 1, 2, 3, 4, dot, dot. And then we have, that's our domain. Okay, and that's just like with the dot, dot, dot. So I'm just like looking at a portion of it. And then here's our codomain over here, which is also the same exact set. 2, -1, 0, 1, 2, 3, 4, dot, dot, dot. But here's what the function does. Function maps each number to double that number. So 0 is going to map to 0. -1 is going to map to -2. -2 is going to map up there to -4. 1 is going to map to 2. 2 to 4. 3 to 6, and 4 to 8, and so on. And sorry, what you get. There we go. What you get is that the range is just even integers, right? So the range is just the even integers. That's a subset of the set of integers. So it's a subset of the codomain. There's the subset set, right? Subset or equal. But in this case, it's not only, it's actually a proper subset of the set of integers, right? Because it's not the entire thing. Right. So the question. Oh, so yeah. So this came to me privately, but I'll share it. Would this be onto and not one-to-one? Think about this. Is this onto? Is this one-to-one or onto or both? What is it? And how do we know the range is all even integers? Oh, good. Both good questions. Let's start with that second question, actually. Although I want everyone to be thinking about if this is onto or one-to-one. How do I know? First, how do I know the range is all even integers? Well, it's because the function is 2 times n. So any output is going to be even because it's 2 times an integer. That's the definition of even, right? And then you can show that every even integer is going to be in there because every possible integer is in our domain, right? Our domain is all possible integers. So what we're seeing here is that the range is only the even integers, right? We're doubling everything and getting all the evens. So that's how I knew that. Does that make sense? Yes. Cool. Yeah. Okay. Yeah. So we've got that range. And then what does it mean when the range, as far as onto and one-to-one, or remember onto is surjective and one-to-one is injective. So vocabulary there. Either one will do. But when we say that the range is like not the entire codomain, what does that mean?
Not onto.
It's not onto. Good. Yes. Not onto, right? Onto or surjective means that it covers, like the outputs cover the entire codomain, which is not true here. We have a bunch of numbers that are not being used. This -1 and this 1, 3, and so on. Those are all not being used, right? That means it's not onto. And then is it one-to-one? Yes, it is.
Yes.
Yes. Yes.
Should we prove that it's one-to-one?
Yeah, that would be good practice. That'd be good measure.
Yeah. Let's prove that. So I'm going to make this a bit smaller, and we're going to do a proof down here. So let's proof that f is one-to-one. Yeah. Okay, so reminder, our f, actually, let's put the proof up here, so that way we can see everything. Reminder that f of n is defined by 2n. So to prove that f is one-to-one, here's what one-to-one means. Basically means that whenever you have 2 inputs that are different, then the outputs are guaranteed to also be different, right? This is so that it passes the horizontal line test, basically. Like, if you think about algebraic functions, it's like passing the horizontal line test, right? If the inputs are different, then the outputs are also guaranteed to be different. Okay, that's one-to-one. But if you take the contrapositive of that, it would be if the outputs are the same, then it must be because the inputs were the same. That's the contrapositive. And often it's easier to prove this version. It's easier to prove that statement. Let me show you how we're going to prove that statement. Proof will begin by saying, let A and B be elements of our domain, which is integers. And then suppose that their outputs are equal. F of A equals F of B. Well, by definition, that means 2A equals 2B. But then I can divide both sides by 2 and get A equals B. I've just proven this contrapositive statement. So you can say, therefore, F is one-to-one. So that is often what a one-to-one proof ends up looking like. You basically start by taking 2 elements that are not specified, right? Because you have to be able to generalize here. You have to be able to you have to be working with two arbitrary elements that are not specified so that you can do a universal generalization at the end and say, like, we don't actually end up writing the universal generalization, but you could. It's kind of a key part of the logic here. Like, this is true for all elements, right? Whenever their outputs are equal, they must have been the same element to start with. So that's what I proved. So x squared would not be one-to-one correct, because when you solve, you get plus or minus. Yes, you get a equals plus or minus b. So you were not. So if you try to do it with x squared, you cannot conclude a equals b because of the possibility that a was equal to negative b. So that is, yes, not one-to-one. Yeah. Yeah, let's do the proof that it's, for this one, proof that it's not onto. Would that be good?
Yeah.
Sounds fair.
Yeah, proof that it's not onto is, I think, pretty quick. Proof that is not, that f is not onto. Well, all we need to do, look at our diagram here. Let's take like 1, for example, right? Let's take 1, for example, and see if we can work with 1, because we know that 1 is an example of a number that's not in the range, right? So by our diagram, right? But that's not quite sufficient. Like, we need to write it up a little more rigorously. Okay, we can't just say, look at the picture I drew. 1 isn't in the range, you know? Like, well, okay, yeah, but okay. Let's let a, okay, put it this way. Let's suppose there exists an element a in the domain, which is integers, right? Such that f of a equals 1, okay? Which is in the range, sorry, in the codomain. 1 is in the codomain, right? Suppose there exists an integer such that f of a equals 1. Well, then 2a equals 1, so a equals 1/2. But this contradicts a is an element of the set of integers, right? Because 1/2 is not an integer. Therefore, 1 is not in the range. So f is not onto. That's all we needed, right? All we need is to show that there's at least one element of the codomain that's not in the range. And I just happened to pick 1. You could have picked 3 or -1 or -3 or any other odd number, and you would have gotten the same result, because when you divide it by 2, the resulting fraction is not an integer, which contradicts your assumption that it was in the range. It's kind of like saying, let's suppose this is in the range, then f of something has to equal it. 2a equals that odd number, but then a was not an integer. Contradiction. Oh, never mind. So it couldn't have possibly been in the range. Therefore, it's not onto. That's the idea.
So you pick a number that you know is not being used, and then you show that it's not an integer.
You show that that number, it can't possibly be in the range, because in this case, and one way to do that, this is just one way to do that, but one way to, like, a nice way to do that is to assume it is in the range and then find a contradiction from that. So you're proving by contradiction that it's not in the range.
Makes sense.
Yeah. Yeah, I think that's the same. Okay, let's see. So that was good. I'm glad we went over that. This is the kind of proof that could be on the test tomorrow. Okay, this is like, oh, these are pretty short proofs that deal with, you know, deal with functions. These aren't as long as some of the ones on your assessment. These are pretty straightforward proofs. So yeah, I would say these are fair game like this. Okay. What do I want to do next? So should we turn our attention to 2.5 now? There were a few questions on that. One request was just to review 2.5 in general. I'm going to begin. I could do that, but let's begin instead with the specific problem that was requested, which is 2.5 number 18. But then from there, if there's any after that, if any more questions about it, we can do those. Okay, is everyone comfortable if I go ahead and clear the board now? Is that cool?
Yeah.
Okay, here we go. Remember, this is being recorded, so I'll put this up on YouTube later as well. That green, back to blue. 2.5, number 18, show that if A and B are sets with the same cardinality, then their power sets have the same cardinality. If A and B have the same cardinality, which is cardinality of A equals cardinality of B, like this, then their power sets have the same cardinality. Ooh, this is a good one. It's a tough one. Okay, here's what we can start with. We're going to assume A and B are sets with cardinality of the same. Then there exists a function f from A to B that is a bijection. So therefore, it's going to be one-to-one and on injective and surjective, right? So that would be this is like the definition of being the same cardinality, right? That there exists a function. So the proof of this is definitely going to rely on the existence of this function. So we need to assert the existence of this function, give it a name. I'm going to call it f. F is the bijection that maps A to B, and therefore F inverse maps B back to A.
So a question here is, this is asking for the size of these power functions. You wouldn't be allowed to say that, well, the size of a power function is 2 to the n, and n is equal to the length of A.
Actually, that's a fair point. My only objection to that is that if these sets are infinite, that's a little bit ambiguous. What does it mean? So actually, in fact, there is this theorem. Okay, I'm just going to go off to the side here for a moment to talk about this. There is indeed a theorem that says, if cardinality of A equals n, then the cardinality of the power set is going to be 2 to the n. That is true. If it's finite, if say n is, if A is countably infinite, then actually its cardinality is represented by this Aleph null, which is the first infinite cardinality. It's the size of the natural numbers or the integers. And then the size of that power set turns out to actually be 2 to the Aleph null, which is equal to the size of real numbers. So this is the cardinality of the real numbers. It's this. So if you take a countably infinite set and you take its power set, the power set of that set will be uncountably infinite, the same cardinality of the set of real numbers. That's proof. So that is actually sort of a consequence. That's a theorem. That's sort of a consequence of Cantor's theorem, which says that when you take a power set, the resulting set is always bigger. Like bigger in the sense that it actually has a bigger cardinality. It has to get bigger. So if you take a countably infinite set and you take its power set, like the power set of the integers, guaranteed that's going to be uncountable because it has to be a larger cardinality. So this notation is sort of used for that, but infinite sets in general, I would be a little bit cautious about relying on this 2 to the n theorem for infinite sets because it's sort of unclear what that means. For like what's 2 to the power cardinality of the real numbers? Like, what is that? You know, it's a little bit unclear, and that's because of that continuum hypothesis, which is like this proven to be unprovable. So it's this like sort of mysterious like unknown in math that we just don't even know what to do with. So I would avoid relying on that theorem unless you know for sure that the sets in question are finite. Then you can use it. So yeah, so what I would do is rely instead on this idea of a function f, and what you want to do is you want to use that function to somehow build a function g, which is going to be a bijection for the power sets. And I think it's pretty straightforward. Basically, all you need to do is think about how, like, say you have an element, say x is an element of the power set of A, then, you know, x is going to have some stuff in it, or it might be empty, but it might have some stuff in it, like x1, x2, x3, ... whatever. All you need to do is map all of those elements to B by, you're going to do like g of x is going to equal f of x1, comma, f of x2, comma, f of x3, and so on. This is the idea, right? You're going to create a function which maps from the power set of A to the power set of B. So it takes a subset of A and it spits out a subset of B by just taking all the elements in that subset and mapping each of them over to B individually with the f function, which you know exists, right? Because you know a bijection exists. So you're mapping them over with f. And then you would just need to show that that function is going to be a bijection on the power sets. This is a longer proof than I want to do right now. So I think I'm just gonna leave it here with this is like, this is how you will define your G, right? You're gonna define G from power set of A over to power set of B by this, you know, whenever X is an element of the power set of A, if you sort of like this idea, you basically define it like this. You define your output from G like that. And it's going to map the empty set to the empty set, and it's going to map the entire set A to the entire set B. You'll be able to show that it's a bijection, but it's kind of a longer process. Okay.
So it doesn't really fit to show sets where you know the numbers in them and then you know how long they are. It doesn't really fit to show a proof like that.
Yeah, that would not be a proof. Since this is a statement, it makes a claim, a very broad claim about any two sets A and B. Any two sets A and B that are the same cardinality, right? Like, you can't just say, hey, look at this set A and this set B that are the same. Like, it's totally useless from the perspective of proving something. Say something like, let A equal xy, B equal 1, 2. And then show, and then like demonstrate in that situation that the power sets are the same size. Like, all you're doing is confirming this claim is true for one particular example, which proves nothing. I mean, it doesn't prove nothing, I guess. It proves that it's true for that example, but it doesn't prove the claim, which is that it's true for any example, right? So whenever, basically, I mean, one of the really key, like, broad ideas about proving things is that, like, if you're trying to prove a universal claim that's applied to all elements of some domain, or like any two elements of that domain or whatever, it never actually is sufficient to just show that it's true for an example, or even two examples, or even three examples, or 100 examples. It's not even like, if you can't show that it's true for an infinite number of examples, right? So if your domain is infinite, there's no way you're going to prove it using examples. I mean, I guess if your domain only had 5 things in it, then yeah, you could prove it's true for each of the 5 things individually, and that would work. But that's rarely the case. So I see this a lot, but like don't do this, right? This is not actually helping you at all in the proof.
Right. When I was doing the problem, it just didn't occur to me that I was supposed to use a function. So it really threw me off.
Yeah, that's very reasonable. And I mean, Scott's approach about using the 2 to the n theorem is a very good idea. And like I said, that would totally work. 2 to the n equals 2 to the n. That works if it's finite. But with infinite sets, I would not use that theorem because of the continuum hypothesis and the ambiguity that it introduces. Oh, yes, sorry. This was 2.5 number 18. I said that and I forgot to write it down. Let me get that written so that people watching this later know what the heck I'm talking about. Isn't this number 18? Yeah. Yeah.
Could you quickly go over like finite, countable, infinity, and the uncountable?
Yes. Is everyone all right if I go ahead and clear the screen? Here we go. I'm going to do this. Yeah. So finite. Summer, did you say finite, countably, infinite, and uncountable?
Yeah.
Yeah. Yeah. So finite is any actual finite number that's like, it doesn't, even if it's really big. So one of the examples from the assessment. Well, I won't necessarily do the assessment right now, but for example, take example like the number of stars in the observable universe. Okay, the observable universe is finite, right? We have a finite amount of universe that we can observe from Earth. So the number of stars in that is finite. There's a finite amount of matter in the observable universe, right? It's finite. So it's very big, right? The number of atoms in the Earth is still finite, right? Any small number, like, the number of people in a marriage, 2 or maybe 3 if you're, I don't know, I'm recording, so I won't make any silly jokes. That's a finite number, right? Then there's infinite, and infinite is on a whole other level, right? So the smallest type of infinity, let me write the cardinal numbers here that you could have, all the way up to like 100, 1,000, etc. But then you've got infinite. And so the smallest type of infinity is countable infinity. And countable infinity is represented by this number, Aleph null, which is this is the size of the natural numbers, or the size of the integers, or the size of the positive integers alone, or like the size of the rational numbers. These are all the same size, despite the fact that they're like proper subsets. Like the natural numbers is a proper subset of the integers, and the integers are a proper subset of the rationals. That doesn't actually affect the fact that they are still the same cardinality. There's exactly the same number of elements, because you can make a bijection between them. Like if you take n and map it to 2n, that actually does form a bijection between like integers and even integers. That's going to be 1 to 1 and on to. So there's the same number of integers as there are even integers, despite the fact that it feels like there should be more integers when you include the odd ones. There's not more. Anyway, that's countable infinity. Then we have uncountable. I think I spelled that right. Uncountable infinity, and that includes Aleph 1, Aleph 2, Aleph 3, etc. What exactly these are is unknown and unknowable, but somewhere in here, probably here, but maybe not. We have this cardinal number called C, which stands for continuum. And it is the size of the real numbers, which it turns out is also the size of the power set of the natural numbers. I never told you that before, but I'll tell you it now. And that is uncountably infinite. It's uncountably infinite. It's this number of real numbers, because as soon as you start including irrational numbers, you have an uncountable infinity, because irrationals are more numerous than rationals. So this is also the same size as like an interval, like any interval. Because as soon as you're including like an interval of the real number line that includes a bunch of irrationals, you immediately have uncountable infinity. So
and that would hold true whether you have the inclusive or exclusive. So the parenthesis or okay.
Doesn't matter if you're including the end points or not, because it's kind of like as Steve, what's that guy's name? Michael Stevens. As Michael says in the Vsauce video, if anybody has watched that, he says infinity minus 1 is still infinity, which is sort of like not quite like a correct way to say it, but it gets the point across. If you take an infinite number of things and subtract 2 of them, you still have the same cardinality that you had before, because infinity is like robust. You can't decrease it just by taking away a few elements, you know? So like if you have this uncountably infinite interval, if you take away the endpoints 0 and 1, you only took away 2 things. You definitely still have the same cardinality. It's sort of impervious to that sort of thing.
I guess my follow-up question is, how does the Cartesian product affect how countable something is? Like if you take the Cartesian product of something that's countably infinity, how does that change?
Yeah, so one of our theorems is about infinite cardinalities, at least for countable infinity. So for Aleph null, countable infinity, put it this way: if A and B, their cardinalities are both equal to Aleph null, then so are a union B and a cross B, or a Cartesian product with B. Those are also always going to be countably infinite as well. So that's sort of like the rational numbers are kind of like the integers cross integers, right? It's kind of like a Cartesian product of integers. Similar. And it's because of the pairing, it's like A divided by B, like it's sort of like a pair, like an ordered pair of integers in a way. So it's countable. Does that answer your question?
It does.
Similar with like the real numbers, right? If you take 2-dimensional real space, like the 2-dimensional space in which we graph functions in algebra class, or like the 3D space that you graph surfaces in multivariable calculus, when you take a Cartesian product of R, the real numbers, with itself to get 2D or 3D space, it still has the same cardinality that it had before. Like that's still going to be the same uncountable infinite cardinality. Like the number of points in the Cartesian coordinate plane is still uncountably infinite, and it's the same as the number of points on a real number line, because of a similar theorem about it like this. With finite sets, the Cartesian product does get bigger, right? With finite sets, you can obtain the cardinality by multiplying the A times B cardinalities together. But infinite sets doesn't work that way.
Could I ask about the group situation with the project?
Let's hold off on that. I do want to get back to that, but let's hold on off on that for now. Now, Mark, you wanted to ask a question about chapter 6. Let's go ahead and squeeze that in.
All right, it's chapter 6, section 6.3, problem 39. So basically what I'm trying to figure out is how to actually use the formulas so you can deal with like giant sets of combinations.
Yeah, because it's too big to just count by hand, isn't it?
Yeah, some of the other ones I tried to count by hand because there was enough, and then I could use the combinations from all the ways. But yeah,
We're talking
this
about-
one's too big.
Let me write the problem up so everyone knows what we're doing. Bit strings of length 10. So long enough that you don't want to do anything by hand. You don't want to like exhaust a bunch of like map out all the different possible combinations and stuff. How many bit strings of length contain at least 3 ones and at least 3 zeros? I'm not sure I'm going to be able to solve this super quickly. Let me think about this. You have 10. You have 10 spots. How many bit strings of 10 of length 10 contain at least 3 ones and at least 3 zeros? Here's a thought. I think the best way to approach this is to say this is the set A. I think the best way to approach this is going to be like that idea. Basically, let's count this by, instead of counting this, let's count the negation of this. So like the complement of this set. We're going to count the negation of this and then subtract that from the total number of bit strings of length 10. So if it doesn't contain at least 3 ones and at least 3 zeros, then it must contain either 2 ones, 1 1, or 0 ones. And if it only contains 2 ones, then it must contain at least 3 zeros. So, you know, like what we're going to end up with is either it's going to contain fewer than 3 ones, or it's going to contain fewer than 3 zeros, or both. I'm sorry, but not both, because it can't be both, because then we'd only have 2 ones and 2 zeros, and that's only four bits, right? So that's like not long enough. So if you're fewer, so I would say here's the idea. I would say so let's count fewer than 3 ones would be counted by saying 10 choose 2, which is the number of ways to make a bit string with exactly 2 ones in it. Okay, so this alone, that is the exactly 2 ones. And the reason we know that is because once you've picked the locations, so the 10 choose 2 is just choosing which 2 locations your ones are going to be in. And then once you've done that, now all the others are automatically zeros. So there's no further counting or multiplying that needs to be done, right? So just that. And then you can add to that 10 choose 1, which is actually just 10. But that's 1 1. And
Is this permutation formula or combination formula?
This is combination. I'm using the binomial coefficient notation for it, the like n choose k or n choose r, but this is combinations. Counting combinations here. Like 10 choose 2 is the number of combinations of length 2 coming from 10 choices. And here the 10 choices are the positions, like the 10 different slots in which we can insert ones and zeros in this string. So 10 choose 2 plus 10 choose 1 plus 10 choose 0. So this is, you know, no ones. So this right here, so adding these things together would give you the number of different ways of having, like the number of different bit strings with fewer than 3 ones. And then I would argue that the number of bit strings with fewer than 3 zeros is going to be exactly the same number, because you can just replace all of the zeros with ones and all of the ones with zeros and obtain the other ones, right? You can just like swap the ones and the zeros around. And there's not going to be any overlap, because when we have fewer than 3 ones, we have more than 3 zeros by necessity, given that the length is 10. And so flip that around. If you have fewer than 3 zeros, you're going to have more than 3 ones. Again, by necessity, or at least 3 ones. So I would say the A complement we're looking for here is going to have that cardinality is going to be 2 times this 10 choose 2 plus 10 choose 1, which remember 10 choose 1 is going to equal 10, and 10 choose 0 is going to equal 1. Those are the last two on the like the Pascal's triangle. The last 2 entries in that row are going to be 10 and then 1. Just like the first 2 entries are going to be 1 and then 10. That and whatever 10 choose 2 equals. I don't remember what 10 choose 2 equals. Oh, thanks, Abdullahi. It's 45. Sweet. Thank you. So that's 45. 45 plus 10 plus 1 times 2. That's a total of 40, 55, 56 times 2 is 112. That is the complement of our set. This is the number of things that don't satisfy this condition. So now we have to take the total number of possible bit strings of length 10, which should be like 2 to the power 10, I think, right? Because every bit can be either a 0 or a 1, and you're making all the different possible choices. Is that right?
Yes, yeah, 2 choices for each one, 10 possible, 10 areas.
Yeah. So then minus that 112. So this is this 1024? Someone said 1024 minus 112. Is that right? Whatever that is. 912.
It's 912.
Yeah, there we go. I was able to do it, and it's only 1053. Not bad. So that's that counting problem. Yeah, it's this. I love these ones where you count the complement instead of the original set. You do like, what if I negate this statement? Then that makes it easier to count, and it's easy to count the whole universe, the whole like universal set, right? Because it's like all the possible bit strings of like 10. That's easy. So then you just subtract and get the answer. And I just think that's a lovely backwards, like coming in the back door kind of approach to counting something like this.
Yeah, it's certainly not an approach I was expecting to use at all to figure those ones out. So I'm just kind of shaking a bit, like how, like, I mean, this pretty close to the test here. So I'm just kind of like, well, all right. Are these the kind of ways that I do it now, I guess? I'm not sure.
This is the kind of thing that, this is certainly the kind of thing that could be on the test. Now that you've seen it, and this is very similar to something that's on the assessment, actually, very similar to some of the ones on the assessment. I have ones about bit strings. I think I made the bit strings a lot smaller, like shorter.
Yeah, and that's why I was able to finitely count them. And so that's not really going to work with some of the other problems. I know that much. But.
Right. Yes. The approach where I generally don't. Yeah, I'll give full credit because I didn't say you couldn't, but I generally advise against these kind of exhaustive methods of just listing out all the different possible positions or something like that. That is not a great approach because it doesn't scale up very nicely.
So we would use the idea of sets to figure it out.
It's useful to talk about it in terms of here's a set and here's the complement of the set. When you're doing this subtraction idea, like this sort of take the negation, which is like taking the complement of that set inside the space, the universe of all bit strings of length 10. It's just useful to think about it in terms of sets and cardinalities of sets, and you're doing this kind of complement thing and then subtracting that off. I wrote it, and I just realized I wrote something here. I wrote the size of the universal set minus the complement, but actually this is the same as this, this is actually the calculation that I did technically. So I should have written it that way. Sorry. That is because you see I did the 1024 minus 112, which is more so this idea. So that's what I meant to write. Sorry. But yeah, now that you have this idea, to me, it's just like a tool in your toolbox that like every now and then you're doing a counting problem and you're like, this seems hard to count. Maybe if I just negate it, it'll be easier to count. And then I can do that subtraction thing. So just keep that in mind, Look at the negation sometimes and think, would that be easier? And if it is, well, I do it that way.
Right. So I was assuming you would just use the formulas like the combination and permutations in this section and not worry too much about sets. So I was just wondering how you could possibly do it that way.
I mean, we did use combinations here. We did the 10 choose 2, 10 choose 1, 10 choose 0, right? Like I did do those, but then this is also implementing ideas from section 6.1. So the subtraction thing comes from section 6.1 along with using the addition rule and that kind of thing. That's all coming from 6.1. This is building on previous sections then. Okay, I'm going to stop recording, but then I'm going to answer the question from Mitch about